Hello. This lesson is on Ohm's law and the power equation. There in green you can see Ohm's law where E equals I times R. E equals volts, I equals current or flow in amps, and R equals resistance in ohms. Ohms is often written with the omega symbol that you see here that I'm pointing to. So another way to write the equation, although it's not accepted by science, is volts is amps times ohms. The second equation we're going to look at is the power equation. This one uses some of the same equation symbols, such as E for volts and I for amps, or current, which is the amount of electron flow. But it also says that P is power, which we think of as watts. And if you've ever changed a light bulb, you may have noticed that it says a certain number of watts. We've discussed watts a little bit in the sense that we've burned up a resistor. Some of these smaller resistors that you see here, these are quarter-watt resistors. They're not quite as powerful as some of the larger resistors that you see here. One thing that's easy to get confused about is to think that it's the physical size of the resistor that determines its resistance. In other words, how much it wants to stop or let flow go through. Now in these cases you have on the left a series of bands which indicate the resistance. These are the quarter-watt resistances, and they're listed as 560 ohms. This is the larger one, and it's a brown, black, brown, and I believe that this one is a green, blue, red. I'll double check those later, but it's those color codes that actually determine the resistance. What I want you to think about is that you can have a hose of a certain diameter that lets flow through. The bigger the hose, the less resistance. But if the hose wall, if the rubber is very thin, then under the right amount of pressure, the flow could burst the hose. So here again is the smaller one, which is a quarter-watt resistor. It's labeled as 560 ohms, and as the meter shows, it's within the 5% tolerance. It's reading 553 ohms. That is a lot to take in, but basically it's reading 560 ohms nominally on a quarter-watt resistor. This one, the brown, black, brown, should be reading 100 ohms. If I follow that all the way up to this meter, it's reading 98 ohms on a 2000 ohm setting. So think of that as nearly 100 ohms with a thicker amount of wall keeping the resistor from burning up. So this one is 560 ohms, again, on the 2000 watt setting, reading 553 ohms. We're going to do some experiments with these and see what happens. These are the resistors we burned up in class. Clearly you can see the tape actually caught on fire. This is supposed to be a 10 ohm resistor. I don't know why it's reading 11, but it is reading the brown, black, black. That would be 10. The 5% should be half of an ohm difference, and why it's reading 11, I don't know. But let's look at what happens with the math. I happen to know that I have a 12.7 volt battery. I have a current, and I have a resistance of 11.3 ohms. if I divide both sides by 11.3, clearly I get something over 1 amp. This crosses off, this crosses off, and let's just arguably say that this is 1.1 amps. I'm just guessing, and it doesn't really matter for the purpose of what we're doing. Remember, the power rating of this resistor is 1/4 watt, so it can't exceed more than 0.25, and that's got to equal my voltage times my current, which I've estimated at 1.1 amp times 12.7 volts times 1.1. Well, clearly that's going to equal about 14 watts on a 1/4 watt resistor. Basically, this never stood a chance. It was going to burn up. This is a lot of math, but my point in doing this is to prove to you that algebra matters. Let's see what happens with a manageable resistor. Let's try to see what happens if we use the 560 ohm resistor, which is reading at 553 ohms, on a battery that's reading 12.7 volts DC. Now what's interesting about this is that it's reading positive because the black is on that side and the red is on that side. If I were to switch these, that would read a negative 12.7, but for a resistive circuit that wouldn't matter. Going back to our equation, if we follow Ohm's law, E equals I times R, and I have a resistance of 553 ohms, then that cancels out, and when you take 12.7 volts and divide by 553 ohms, our current is equal to 0.0229 and some remainder of amps. Using the power equation, power equals E times I, 12.7 volts times rounding off to 0.023 amps. Our wattage is slightly over the 1/4 watt, 0.291 watts. In theory then, this 560 ohm resistor applied to 12.7 volts should not last very long. I'm not quite sure if that's going to work, but what I am going to do is I am going to see if it heats up using this gun. Right now the temperature of this table is 72 degrees. We'll see what happens in just a minute. What I'm going to do now is I'm going to take my 12.7 volts and apply it as what's called electrical potential across my 560 ohm resistor. I go to one side, move it onto something that I think will be safe to put it on, and then I apply the other 12.7 lead to the other side, so you can see that the resistors that I'm looking at here are 74 degrees. The resistor to which I have applied the voltage is 73 degrees. I don't see it getting warmer. As a matter of fact, let me double check. It's 74 degrees or 73 degrees. Might be getting a little hotter. Since it's such a low temperature, I'm going to touch it. And I can tell you it's only mildly warmer than some of the other ones. Believe me. Oh, there it is. It's getting a little warmer now. Let's see what happens. A lot of this depends on the time that you apply it. So if I go to here, I'm still at 73. So it seems that while this is a quarter-watt resistor, and while the numbers would seem to indicate that it's taking more than a quarter-watt resistor, it's not getting warm. And it's able to take a little bit more than you might have otherwise thought. I'm at 74 degrees on this resistor, and I am at 73 degrees on the other resistor. Kind of hard for me to show you all of this, but that's what I'm getting. No real change. So here's the experiment we're going to run. We've got a 12.7 volt battery. It's hooked up across the battery, and all it's doing is it's reading the electrical potential as if you were reading the tire pressure of a car. There's no flow. It's just like you're using a tire gauge to say there are 12.7 volts. That 553 ohms, exactly what we've measured before. That 553 ohms right there is like the hole that you would use to fill up the air with through the air hose. The bigger the valve, the less resistance. So we're going to look at it as a schematic. What I've got in blue up at the top is a 12 volt reading that we're going to have here. The resistor that we'll put in here will be 553 ohms. That will not have changed. The battery down here will be 12.7, and the voltage up here will be not the 12.7 exactly, but the voltage drop, what's called the voltage drop across the resistor. The meter that we're going to have here, and I could get a third meter, but we're only going to use two. The meter that we're going to have here is kind of like if you've ever had a bicycle and you've ever taken, well, we did it when we were younger. We would place baseball cards on the spokes, and we would allow this baseball card to make a ticking sound, and the faster you went, the faster you were going, and the more tick, tick, tick that would happen. Everything from this battery must flow through there, and then you can kind of feel the resistance here as if you were holding a door open against the wind. That's what's going to happen here in a minute. So what I'm going to do is I'm going to take this schematic and hook up the whole thing with the meters for real. Here's something to consider. We have this Ohm's Law equation, 12.7 volts divided by the 553 ohms equals 0.0229 and some other number amps. Well, that's got to be rounded off in the power equation because it's just not a workable number when you use calculators. But the power equals the volts times the current, and 12.7 equal times 0.023 amps equals this 0.291 watts. Slightly more than a quarter watt, slightly more than the rating of this 560 ohm resistor. Well, the question then becomes, how do we set this meter? If you'll notice, I've taken away the red. The reason I've taken away the red is so that you can see that on the right there's a V, an omega, and a milliamps. This 10 amps over here is used for this setting only, and we would never use it. If you're reading 10 amps, you're reading some heavy power, and you're reading something that you would read in a car, and it's not likely to happen in this. We've set this to 200 milliamps. If I set it to 20 milliamps, it wouldn't work, and I'll explain why in a second. I'm going to set it to 200 milliamps, and let's re-examine what we have. We have 0, 0.023 amps, which is equal to 23 thousandths of an amp, or 23 milliamps, which is what requires me to set it above the 20 milliamp reading. I'm now going to hook up the entire circuit with the 2 meters. This is very busy, but it's actually producing exactly what I said it would do. It's reading 12.6, now I said 12.7 volts, but I can explain that. And it's reading 23.1 milliamps. And I want you to see what we have here. I'm saying to you that out of my battery, I will have a red cable. To that red cable, I will go to that red lead and into the ammeter. So out of this battery right here, I have a red lead going into the ammeter, coming out with a green lead here from the other end of the ammeter. The ammeter runs here and is actually carrying current through to the black one. And the black is going back to the other side of the battery. Like I'm saying, the black is going to the other side of the battery. Now, what I have up here reading the voltage drop of 12.6 volts appears to be a yellow and a white cable. That's reading the 12.6 voltage drop. It changes a little bit, but as you can see right here is my voltmeter. Here are my 2 leads, and I'm reading my voltage across my resistor at 12.6 volts. Now what I'm going to do is I'm going to take that off, but I've proven to you that it's 12.6 volts on a 12.7 battery, and by my calculations I was supposed to get 23.1 milliamps. We'll review the math one more time, but let's remember 12.6 volts, 12.55 volts. That actually gets interesting. And rock solid 23.1 amps. Let's see again what happens if I measure the battery by itself though. This is where I wish I had a third meter. All I've done is momentarily hooked up the battery, not across the resistor to check the voltage drop, but I've measured the voltage of the battery. So the question then becomes, where does the 0.1 volts go? Well, the answer is, the way I like to explain it to middle school students is it's electrons filling up the wire and taking a little bit of the heat, just as if you'd have a new garden hose hooked up to your house and it took a little while before the flow would come through. That 0.1 volts is, think of it as the electrons filling up the wires before it can get through to the resistor. I'm pretty happy with the experiment so far, and I'll try to run the numbers for you. So let's see if we can compare theory to reality. What I said to you is that you would have a 12.7 volt battery, which we did. I said to you there would be an ammeter reading that should have been about 0.0229 amps, or 22.9 milliamps. This, if we had written it as milliamps, would have been 22.965 milliamps. What we had in reality was volts equals amps times resistance, E equals I times R, and our reading on our ammeter was 0.023 amps. Because you have to put in the numbers as the decimal, you can't enter it as 23 milliamps, times 553 ohms, which is 12.719 calculated volts, versus the actual voltage drop that we got. And quite frankly, I'm not capable of explaining the difference except to say that perhaps it's the meter, but generally speaking, that's very close to what we had as a voltage drop across our 553 ohm resistor. So all of this is assuming that the 553 ohms that we read was accurate. Okay, the meter itself could be wrong, but if you look at the power equation where you have volts times amps, you have the voltage drop, not what I thought would have been across the battery, but the drop of 12.6 volts times 0.023 amps, 23 milliamps, gives us a wattage of 0.2898. Remember, this was a quarter watt resistor, which should have come out as 0.025 watts. Clearly, the people who make these resistors make them with a little capacity to spare. In other words, they don't immediately burn up at a quarter watt. That's different than when you applied the 14 amps across a resistor that was only expecting, a very small, minute amount of amperage. So this resistor never stood a chance, whereas these 560 ohm resistors could take a little bit more power than you might have otherwise thought by calculation. So basically, I'm very pleased. I'm going to give each group of you 2 voltmeters, a resistor, and we're going to figure out a way to hook up the battery across this. You can expect to do some calculations and then turn in your answers through Edmodo, through a worksheet. But if you can understand this kind of algebra and theory and electricity in middle school, then I sincerely recommend that you take the science, technology, engineering, and math completer courses at the high school. I hope you've enjoyed this. Thank you very much.